So good morning. This is in continuation of my previous lecture on solving linear differential equations with constant coefficients. We are enumerating the cases of Q given a following particular form. So three forms we have discussed. If Q is exponential AX, what we write. If Q is sine or cosine function, what we write. And then finally we have done that if Q is an x power xn, for example, then how to write the particular integral. Now in the case 4 and case 5, these are the two cases, case 4 and case 5. Q takes the form of exponential AX into V, where V is a function of x. And if this thing happens, then we write the particular integral as, we bring this on the left of the operator, exponential AX, replace d in this fd by d plus a, and then apply 1 upon fd plus a on v. Whatever this will give you, multiply this with exponential ax, that will be the particular integral. Second and fifth cases, that 1 upon fd of xv, where this v is again a function of x, so it takes care of functions like x cos x, x sin x, and things like that. So this will be x on the left of the operator, 1 upon fd, and 1 upon fd acting on v, and then what we do, we differentiate this polynomial in d with respect to d, and then operate the resulting operator on v. So I'll explain this, both the cases, with the help of examples. Let's look at this example. d4 minus 1y is exponential sin x, exponential x into sin x. So this is the fourth case where a is 1 and v is sin x. So by now we know that if this is the equation, then the auxiliary equation is m4 minus 1 equal to 0. Its roots are plus minus 1 and plus minus iota. So the complementary function will be c1 exponential x plus c2 exponential minus x plus c3 cos x plus c4 sin x. Now what will be the particular integral? This will be 1 upon d4 minus 1 exponential x into sin x. By the help of case 4, I take this exponential x here, replace in this d4 minus 1 d with d plus 1. So this is 1 upon d plus 1 4 minus 1 on sin x. When you expand this using binomial, so you will get d4 plus 4d cube plus 6d square plus 4d plus 1, and then there is a minus 1. So 1 cancels, and you will have something like this to be 1 upon this to be operated on sin x. So we know that if this is something which is operating on sin x, then I will replace d square by minus a square. So it is here 1. So d square is replaced by minus 1. When you replace d square by minus 1, d4 becomes 1, 4d cube becomes minus 4d, plus 6d square becomes minus 6, because this d square is minus 1, and this is 4d as it is. This 4d cancels with this 4d, and you are left with 1 minus 6. So you have that particular integral is given by exponential x into sin x divided by minus 5. So the complete solution is given by this complementary function plus minus 1 by 5 exponential x sin x. There are some more results which I can draw from case 4. Look at this, 1 upon d minus a exponential ax. I have told you that whenever we apply on exponential ax on this fa should be non-zero, but it is becoming 0 here. If you put d equal to a minus a gives you 0. So you can't apply the case 1 technique here. But if I write this exponential ax as exponential ax into 1 and then use case 4, then this exponential ax comes on the left of the operator and d is replaced by d plus a. So you have exponential ax on the left, 1 upon d plus a and minus a. This a cancels and you get exponential ax 1 upon d of 1. D is differentiation, so 1 by d is integration. So 1 by d of 1 is x. So you get that this is x times exponential ax. So if we are having 1 upon d minus a of exponential ax, the particular integral is given by x exponential ax. Similarly, this case 1 upon d square plus a square of cos ax. Now cos ax you can write as real part of exponential iota ax. Exponential iota ax has real part as cos ax and imaginary part as sin ax. So I will find a real part of 1 upon d square plus a square on exponential iota ax. Now d square plus a square can be broken in two parts as d minus iota a and d plus iota a. D plus iota a doesn't create any problem because when you put d as iota a, this will give you 2 iota a. But this part will create problem. But that will be solved by this formula. So you have that this is real part of 1 upon 2 iota a plus iota a, and 1 upon d minus ia of exponential iota ax. Now you apply this formula and you will write this that this is 1 upon 2 iota a x exponential iota ax. Now you want the real part of it. So this will be open up as cos ax plus iota sin ax. So this iota will cancel with the iota of the sin ax. So the real part will be x by 2a sin ax. From here we can also find the corresponding formula for d square plus a square sin ax. So I will write this. So you have 1 upon d square plus a square sin ax is imaginary part of 1 upon d square plus a square on this. And doing exactly in the same process, you will end up at imaginary part of 1 upon 2 iota a and x exponential iota ax. Now this is imaginary part of 1 upon 2 iota a x cos ax plus iota sin ax. So what's the imaginary part? This iota cancels with this, gives you real part, which is here. But the imaginary part will come here. This x cos ax and 2a. This iota comes in the numerator. So the imaginary part is minus x by 2a cos ax. So we have this formula that this is minus x by 2a cos ax, or whatever I have written here, that 1 upon d square plus a square cos ax is plus x by 2a sin ax. So this we need in some problems, these formulas, because case 2 doesn't work here. D square when you put as minus a square, this will give you 0. So you can't get these things from using the second case, but using this case 4 and this application of it, we can find what happens when the particular integral involves terms like this. I give an example of the case 5 also. So I am rubbing this off. Let's look at this. D square plus or minus it is simple. On the left hand side, d square minus 1 y is x sin x. So you have an example of what happens when this is x into a function of x. So nothing to be explained about this auxiliary equation. It is m square minus 1 as 0. The roots are plus minus 1. So complementary function is c1 exponential x plus c2 exponential minus x. Now I come to applying the case 5. So particular integral is 1 upon d square minus 1, and you apply this on x sin x. So x sin x will be x here 1 upon d square minus 1 on sin x, and then differentiating this 1 upon d square minus 1 and then applying it on sin x. So the first term is x Now 1 upon d square minus 1 on sin x. Here a is 1. I replace d square by minus a square. So d square is minus a square. This is 1 upon minus 1 minus 1 minus 2. So this is minus x by 2 sin. Now come to the differentiation of this. This is d square minus 1 minus 1. So this will become minus d square minus 1 whole square, and differentiation of this, which is 2d written on sin x. So d square minus 1 inverse, so minus d square minus 1 minus 2, 2d, we get this. Now apply this again, d square as minus 1 here, you will get minus x by 2 sin x as it is, then minus 2d as it is, and this is minus 1 minus 1, so minus 2 square on sin x. So this is 4, so this is minus x by 2 sin x and minus 1 by 2, and d of sin x is cos x. So this was your complementary function. This is the particular integral which I have obtained. The complete solution is y c1 exponential x plus c2 exponential minus x by 2 sin x and minus half cos x. This solves this linear differential equation with constant coefficients. So I stop here and give in the next lecture another method which is known as method of partial fractions. Thank you.